Hey everybody, time for another video. This time we're going to be using an equilibrium expression to solve for Kc. So let's get a balanced chemical equation up here, and we have 2NO gaseous plus some oxygen gas, and it's going to be a reversible reaction with 2NO2 gas. And we're going to start off by writing our equilibrium expression. So hopefully everyone remembers how to do that by saying that Kc is going to equal the concentration of our product, NO2, and this concentration, that's what the square brackets mean, concentration, has to be raised to the power of the coefficient in front of the chemical. NO2 has a coefficient of 2, so it has to be raised to a power of 2. This is going to be divided by the concentration of our reactant, NO. If that NO has a coefficient, which it does, it's a 2, we need to raise this to a power of 2. Multiplied by our other reactant, the square brackets mean concentration, but the oxygen doesn't have a coefficient other than 1, so we can just leave this 1. Now the question has to provide you with a little bit of information. So solve Kc if at equilibrium. What that means is we've taken some flask and we've mixed these gases up and we shook it and played with it and let it sit on the counter for as long as we want, and then it stops reacting. Now that it's stopped reacting, we measure what's inside it. So if at equilibrium we have the following concentrations. Note that we have to be provided with concentrations because that's what the equilibrium expression uses. So if you've been told that the concentration of nitrogen dioxide is 4.5 moles per liter, and the concentration of nitrogen monoxide is 0.8 moles per liter, and the concentration of oxygen is 0.5 moles per liter. Now, if you're a clever little cupcake and you were paying attention last time, you should be able to see that this reaction looks like it's moved farther to the right. Look at this. We have more NO2, we got 4.5 moles per liter, than our reactants, which are 0.8 and 0.5. And we learned last time that if the Kc value is above 1, it means it's going to shift further to the right. So if we do this correct, we should be expecting a Kc value above 1. Let's go ahead and see what we get. Kc is going to equal, we fill in our concentrations into the equation. The concentration of NO2 is 4.5. I can use these parentheses now because at this point we're working with numbers. These square brackets literally mean that it's the concentration of NO2. As soon as I use 405 or 4.5, I can just use parentheses. Still has to be squared though. Don't forget that. All over the concentration of the NO, which is 0.8, and that has to be squared, and the concentration of the O2, which was 0.5. We clean this up, and we get Kc is equal to 20.25 all over 0.32, and we can finally calculate that, and we should get a Kc value equal to about 63.3. I like it. I like it. That is a good Kc value. We knew that it was going to be a number above 1 because we can see by looking at our concentrations that the products were favored. This reaction was more likely to end up at equilibrium with more products. So equilibrium means it stopped reacting. Where did it end? It ended with these concentrations. This Kc is a value to show us what ratios of products and reactants we will get. I'm going to go ahead and do another one here. Let's move this up and give us a brand new chemical equation, and this time we are going to be looking at 2HF as a gas, and this is a reversible reaction with H2 and F2. We can begin this again by creating our Kc expression. Our Kc is going to equal the concentration of our products, H2, raised to the power of the coefficient in front of H2. Oh, it's just a 1, no worries there. Multiply by the concentration of our other product, F2. Check for a coefficient. No coefficients there, not a problem. All divided by the concentration of our reactant, HF, which has to be raised to a power equal to the coefficient of HF. In this case, it's a 2. We need a 2 there. I'm gonna throw a wrench in our plans, because this time, instead of giving you the concentrations, I'm going to say that in a 5-liter flask, at equilibrium. So we still mix this up. This isn't what we put in the flask. You could put all sorts of things in the flask and shake it and dance with it and like carry it around town and go shopping. And at the end of the day, this is what's left in the flask. We have 0.2 moles of H2. We have 0.3 moles of F2 and 1.8 moles of HF. So that's what's left in our flask at the end of the day. Irregardless of what we put in this flask, we got a 5-liter flask, we're walking around, we're looking cool, people are seeing us on the street and being like, hey, what's in the flask? And I'm like, just you wait and see what's in this flask. It's busy reacting. But at the end of the day, this is what is left in the flask. We cannot fill in this 0.2, 0.3, and 1.8 into our equation, and you know why? This is one of those moments where you like shout it out loud, like you're watching some little children's TV show, and you're like, because it's not the concentration. And I'd be like, yeah, that's absolutely right. That's not the concentration. In order to get the concentrations, concentration is equal to the number of moles divided by the volume. So our concentration of H2 is going to equal 0.2 divided by the volume of our flask, 5. So this one's going to equal 0.04, and our concentration of F2 is going to equal that 0.3 divided by 5, which is 0.06. And sorry, I'll put some units on these. It's molar. Molar means the same thing as moles per liter. Don't forget that. I can use a big M. I can write moles per liter if I want to just save space here. And our concentration of HF is equal to 1.8 over 5, which is going to equal 0.36 molar. Now we have the concentrations. Now we have the concentrations. So we can go ahead and fill those in to Kc. Do you think that Kc is going to be less than 1 and favor the reactants? Or is Kc going to be greater than 1 because this reaction favors the products? Well, look at which ones we have the most of out of these, and you should be able to predict whether we're going to have a little Kc or a big Kc. We fill in our concentration of H2, that's 0.04. We don't have any power here. We fill in our concentration of F2, that's 0.06. We divide this all by the concentration of our HF, and that's 0.36 squared. And we plug and chug and we chuck this into our calculators, and it leaves us with a Kc value equal to 0.0185. If you guessed that Kc was going to be less than 1 because our reactant, HF, was what had the highest amount, you would be correct. So thank you very, very much, and I will look forward to seeing all you clever little cupcakes next time. Cheers!